Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the series of lectures on chemistry of environment. Earlier we discussed about atmospheric chemistry and aquatic chemistry, and from today we are going to discuss about soil environmental chemistry. This soil part is also referred as lithosphere. How atmosphere and aquatic chemistry we discuss, here we are going to discuss about soil, and this is also referred as lithosphere. First we will look at what are the importance of soil. And if you see, this soil is a variable mixture of minerals consisting of inorganic, organic matter, water and air in it, that is normally is soil. And this soil, if you look at it, is capable of supporting plant life on earth's surface as well as contributing to the aesthetic of the green planet, through which we can have a very nice look, as well as plant life is if it is supported there. And the soil also acts as a medium and filter for collection and movement of water. So, water transport is taking place through the soil, and by supporting plant growth, soil becomes a major determinant of atmospheric composition and the earth climate. Okay. Whatever the stabilized earth climate, the weather we experiencing is because of this soil supported by the, and cultivation of land, that is agricultural practices, actually yield food production for our livelihood. This is also comes from soil, and soils are open system that undergo continual exchange of matter and energy with the atmosphere, hydrosphere and biosphere. So, in this way soil plays a very important role for the exchange of matter as well as energy. The soil also acts as a base from which all minerals like gold, silver, copper, everything extracted from the minerals actually available in the earth. And at the same time, the lithosphere also acts as a base in which solid wastes are disposed, and soil is a receptor of large quantity of pollutants such as particulate matter from atmosphere, that is emanating from power plant of smokestacks. This also get deposited on the soil. Also we use lot of fertilizer, pesticide and some of the material for protection of crop. These material applied to soil often contribute to water and air pollution, that is in which soil acts as a base. Therefore, soil is a key component of environment for chemical cycles through pollutants and other things. So, this clearly tells the importance of soil, from which many things whatever essential for us, we get it from soil. Now, before going to this details of soil composition and other thing, how soil formed. This is soil formation is a process by which rocks are broken down into progressively small particles and mixed with a decaying organic matter. This is actually so because of weathering of rock is the main reason for the formation of soil, and this process is not taking place in 1 or 2 years or so. It is an ongoing process that proceeds through the combined effect of mainly 5 soil forming factors, namely it depends on original parent material, climate, that weather, living organism that's actually present in this one, and topography and time. All these things determines the weathering pattern and soil formation. So, this soil formation consisting of, you can say, 3 steps. First, disintegration of the parent rock material, bedrock disintegration is the first one at start. Next, this disintegrated material breaks down into smaller mineral particles, that is the second stage of this soil formation, and the third one is actually organism in an area contribute to the soil formation. As soil continues to develop, layers called horizons are also formed. So, this actually due to the weathering, that we will see what is weathering actually in details, and that leads to from the parent rock material to soil horizons. So, if you look at weathering, that is mainly responsible for the soil formation from the rock, and this weathering is a geochemical phenomena, that is disintegration of rock by water, light, air, and including biological organism is responsible for the formation of soil from rock by the process called weathering. And both physical, chemical and as well as biological also contributes towards the formation of soil. If you look at physical conditions, that is usually wet and dry condition prevailing also responsible for the weathering, and also swelling and shrinking, that is hydration and dehydration of this type of physical process also responsible for physical condition and weathering. Growth of roots and temperature increase also responsible for weathering, that comes into the physical condition in which in a particular locality how the weathering leads to. But more importantly, what is important is chemical mechanism of weathering of rock as major responsible for this, and chemical phenomena consisting of dissolution, solubilization of rock material in water, then precipitation, that is a reverse of it, acid base reaction, complexation, hydrolysis, and redox reactions, namely oxidation as well as reduction. All this process contributes chemically for the weathering of or disintegration of the original rock. And in this actually equilibrium conditions of rock, water and mineral system is maintained in this during this weathering process. So, chemical weathering, as I mentioned before, water is mainly responsible, that is a dry condition, slow, wet is mainly responsible. In fact, a dry condition the weathering is slow. Suppose if it is a wet, water is available, the weathering takes place faster. And water, a chemically active weathering substance, and it holds weathering agents in solutions such that they are transported to chemically active sites on rock minerals and contact a mineral surface at the molecular and ionic level and dissolving them. And prominent among such weathering agents coupled with water are gases like carbon dioxide, oxygen and organic acids, okay, like including humic acid, fulvic acid, and strong acids like sulfuric acid and nitric acids. All this both weak acids that comes from carbon dioxide and organic acids like humic and fulvic acid, usually weak acid and also complexing agent, they also contribute. In addition, strong acids like sulfuric acid and nitric acid, if they have a contact with this soil, that also accelerate the process of weathering. So, water dissolution, solubilization, especially in acid medium, contributed by weak as well as strong acids. As per this equation, carbon dioxide dissolves in water forming carbonic acid. Similarly, sulfur dioxide dissolves in water, sulfuric acid. So, the rainwater is slightly acidic because of the dissolution of carbon dioxide. It can bring the pH up to 5.6. So, that is also responsible for the dissolution of mineral materials originally present in the rock. And acid rain, already we discussed sulfuric acid, that is rainwater strongly acidic. This is normally we call it as a acid rain, that also contribute for the dissolution of mineral materials present in the rock and ultimately goes. This phenomena also explain why the river water rich in TDS than rainwater. Rainwater, if we analyze the TDS, it will be very, very low, whereas if we as a river water TDS or electrical conductivity, usually it will be high. This is because of dissolution action of these mineral acids on rock, ultimately dissolve and bring it to the river. And if we look at the major chemical phenomena taking place on weathering on rock, hydration and dehydration reactions. For example, calcium sulphate takes up water, forms the hydrated molecule. And if you look at this one, ferric hydroxide with the water hydration may lose water. Okay. So, both this the solubilities are different, they also contribute. And dissolution, if you look at it, this calcium sulphate hydrated species undergo dissolution and forms calcium ion and sulphate ion. So, this way it contributes to dissolution or mineral formation. And dissolution with hydrolysis is also possible. If you consider magnesium silicate molecule, especially in presence of carbon dioxide, and that dissolve and bring out the solubilization of this magnesium ion, that is the silicate, magnesium silicate is hydrolyzed and forms water soluble magnesium bicarbonate. And acid hydrolysis is another process through which also it can contribute, and which accounts for the dissolution of significant amounts of especially calcium carbonate material and calcium carbonate magnesium material that is rich in water. That is calcium carbonate, when it is exposed to carbon dioxide, may dissolve, and because calcium bicarbonate is water soluble, whereas calcium carbonate is not water soluble. Same thing applicable to magnesium also. So, carbon dioxide brings out acid hydrolysis and causing the dissolution of the original parent material. Apart from this, oxidation also may contribute. If you look at this iron silicate, carbon dioxide can bring out iron solubilization, and this in turn further undergoes oxidation in presence of molecular oxygen and gets converted to ferric oxide. Original iron silicate material is converted to iron oxide. Okay. So, this also lead to solubilization of the mineral compounds. Complexation also bring out solubilization of the material, and for example, if there is a organic matter is there, its microbial degradation may lead to formation of oxalic acid or oxalate ion. This oxalate ion is able to form complexes with the aluminum, iron, etc. That also brings out the solubilization, because aluminum, iron silicate are water soluble. Okay. So, this silicate originally containing aluminum silicate is solubilized in presence of oxalic acid into its oxalic water soluble oxalate component. So, all these things leads to formation of what is known as soil horizon over a period of time. This happens, and in fact, in the soil profile, if it go into the deep, we can see this is a soil profile or soil horizon, like horizon A, B, C, D, etc. And if you look at it, the top one, that is a soil horizon A or organic origin part, which is rich in soil organic matter, low in inorganic things, low in the sense usually compared to the other horizon. The next one is type B or subsoil. Normally here the organic, if we go bottom, the organic content usually decreases. The C, in which the parent original material, its which disintegrated, that is present in the C horizon, and ultimately bedrock will be present. So, bedrock, that leads to disintegration of the original parent material, which is rich in again inorganic. Organic will be very, very low, and below this topsoil A, soil horizon B will be there. That is actually a subsoil, we call it as a subsoil, that is also will be less in organic matter when compared to the topsoils, that is which is very much important for the growth of plant materials. Next, these integrated material soil, we collectively call it as soil, but based on the size it can be grouped into different materials. So, particle size is one of the primary physical property of the soil, and it is arbitrarily defined as a material with a particle size less than 2 mm. We call it as a soil. And within the material defined, that is soil with a less than 2 mm, there are 3 primary size material categories of the soil in the order of decreasing particle size. Between 0.02 to 2 mm, we call it as a sand, and between 0.002 mm to 0.02 mm, we call it as a silt, and less than 0.002 mm, we call it as a clay. So, soil consisting of 3 particles of this sand, silt and clay in the decreasing order. All the 3 collectively we call it as a soil. And United classification system, they have converted into 4 categories of major soil particles. That is, one, gravel between 2 to 60 mm, it is classified as a gravel, and again they are considered sand, silt and clay as another fraction. So, gravel is a particle size greater than 2 as per the UCS classification of soil. We will see some of the characteristics of the soil. And soil composition we are going to discuss elaborately maybe in the next lecture, and by origining of this various features of the soil color, texture, aggregation, porosity, iron content and pH of the soil are all important soil characteristics. We will see one by one. If it's look at the color of the soil, actually soil has color and possesses a wide range of color in naturally occurring soil material, and soil with significant organic content in it appears dark brown or black in color. Such soils are rich in organic, that is ideal. And the most common soil hues are in the red yellow range, okay, getting their color from the iron oxide mineral that is coating soil particle. So, soil rich in iron oxide usually appears red to yellow, and red iron oxide dominate the highly weathered soil that is actually comes from the original parent material. So, soil frequently saturated by water appear gray, blue or green because it depends on what are the mineral content in it. The minerals that give them the red and yellow colors have been leached away from the original thing, that is iron oxide. Iron material is leached out, the other minerals present gives us various different colors to the soil. And next property is texture of the soil, and it depends on 3 components of the soil, namely soil, sand, silt and clay. These are the 3 things. The proportions actually determines the texture of the soil, and it is a relative percentage of each particle in the soil. And soil contains air also, and generally has a loose structure. If more air is present, that is provide a loose structure, and large particles tend to drain quickly and have lower fertility. The particle size is larger, and through the soil water will drain out quickly and have low fertility value. In this, agricultural crops may not be supported very much. And very fine texture soil, when poorly drained and tend to become waterlogged and not well suited for agriculture purpose again. If the soil is very fine, that will be rich usually in clay, that water drainage is very poor, leading to waterlogging in that area, that is also not suited for agricultural purpose. And soil with a medium texture and a relatively even proportion of all particle size, that is sand, silt, clay, is the most versatile. But what is important for a productive soil for agricultural purpose, a combination of 10 to 20% clay along with the sand and silt in roughly equal amounts and a good quantity of organic materials about 5% is considered an ideal mixture for productive soil. And this soil usually will have voids that fill up air and water. That is a ideal thing. This one is very good for cropping purposes. Aggregation of particles in soil. Usually the individual soil particles tend to bound together into larger unit referred as what is called aggregate or soil bed. These aggregation occurs as a result of complex chemical forces acting on a small soil components, or when microorganism and organic matter in soil act as a glue binding particles together, that leads to the agglomeration of smaller particles. And solid range size of this one, very fine, usually very fine particles less than 1 mm, and to very coarse, that is greater than 10 mm particles also possible. The other properties of the soil are density. That density of the soil reflected that the mineral content of it, whether inorganic minerals are there or organic components are present, that's make up the composition, reflects the density of the particle. And if any given volume of a mineral soil, there is an approximately equal proportion of solid and pore spaces, and in fact the former consists of 45% of mineral and 5% of organic matter, and the latter consists of water and air equally. So, the proportion of air and water should be approximately equal, so as to create favorable conditions for biological activity, that lot of organisms will be present and which is considered to be very good for cropping activities. So, the density usually in the horizon, if you see the top soil always contain rich in organic, the density will be low, and as move down the horizon, usually the density will increase because of the mineral compositions. So, top soil usually because of the organic matter contribution, the density will be a little low. Porosity is another factor which contributes to this soil particle. So, the part of the soil that is not solid is made up of pores of various sizes as well as shapes, and sometimes small and separate, and sometimes consisting of continuous tubes type also. The size and number and arrangement of the soil pores is known as soil porosity, and porosity greatly affects water movement and gas exchange like oxygen, carbon dioxide, etc., with the atmosphere. Well aggregated soil have numerous pores which are important for organisms that live in the soil and require water and oxygen to survive, and transport of nutrients and contaminants will also be affected by soil structure and porosity. So, the porosity is small, transport will be affected, and permeability of the soil is another important factor which contribute to the soil properties. That is, the permeability is nothing but ability of the particular soil to contact water or allow water to pass through. It is probably the most significant single factor in influencing the environmental behavior of the soil. Soils with well developed structure are more permeable than structureless one, and the volume of space created by structural boundaries may be small compared with the total pore volume of the soil, but it can be a major route of water transport. And clay in soil which act as a liner for landfill due to its low permeability. Because of the low permeability, clays rich soil are used as a landfill whenever constructed, and it is a naturally occurring material. And soils with low permeability can become waterlogged. Again, that is also contributed by the clay soil. So, wherever clay soil is there, permeability will be affected, and in fact, the natural clay material is a wonderful liner material for the landfill construction as well as septic tank. So, these soil rich in clay, waterlogging is a problem. That is, its physical and chemical properties undergo drastic change. Oxygen in such soil is used up by this microorganism present originally in the soil that degrade the soil organic matter. In such soils, that bonds holding the soil colloidal particles are usually broken, which causes disruption of the soil structure. So, the soil does not contain the air required by most plant root, and thus it is detrimental to the plant growth. And most useful crop with the exception of rice cannot grow on waterlogged soil. So, these are some of the common issues with respect to waterlogging, but usually the main environmental issue in this type of soil waterlogged area, usually these waterlogged area there is a reduction of P values, because waterlogging prevent the contact with the atmosphere. As a result, it becomes a reducing condition. So, there will be a reduction in the electron activity by the action of organic reducing agent acting through bacterial catalysis actually present in the soil, that brings out this or anaerobic condition is established there. So, this condition what happens is the soil becomes more reducing, and water insoluble compounds like manganese dioxide, ferric oxide actually present in the soil is reduced to water soluble manganese 2 and ferrous, okay. And these mobilize the solubility of these ions manganese 2 and ferric. So, they are leached out and more amount of iron is available in the soil. So, such soils which are enormously high in iron content behave as a toxic to plants at a very high level as per this equation. So, this is a reduction, both insoluble manganese dioxide, ferric oxide are converted to water soluble compounds. So, not only this, even the soil contains suppose arsenic, they are also reduced to highly toxic trivalent arsenic is also possible. If the soil contains pentavalent arsenic, that may be reduced to trivalent arsenic, that is also possible. To sum up, we have discussed about the importance of soil, what are the various chemical processes as well as physical processes actually contributes to the formation of soil, soil horizons, and what are the main properties of soil we discussed, especially in the permeability of water is one of the environmental issues, and which waterlogging is a usual problem with the soil rich in clay, and there we have to take appropriate things. At the same time, the clay materials also used for environmental protections like in the landfill liner to control the leachate, as well as from septic tank clay materials are used as a natural material. With this, we come to the end of this session. Thank you.